Okay, next up we have Charles Radin. Please join me in welcoming.
Okay, I'll be talking about emergent phases in constrained networks, so random networks. So I'll be using one example throughout, though much of what I talk about generalizes quite a bit. As an example, consider the two-parameter family of probability distributions, uniform distributions on networks with given constraints on the number of edges and the number of triangles. So the number of edges, or the edge density, and the triangle density will be the parameters in my distribution. So fix those and look at the uniform distribution with those fixed parameters. Okay? So that family of distributions I'm calling a constrained random network. And by the way, by density, I just mean homomorphism density in the usual sense. For simplicity, it doesn't make a big difference, especially for edges and triangles. So in this example, the set of all possible values of those constraints, the edge and triangle density, which I'll call the parameter space of my model, or phase space, was completed in 2008 by Razboroff to be the interior of this scalloped triangle, complicated triangle. Most of the area is kind of nice, but along here you have, in fact, infinitely many scallops. Everything in the interior of this is achievable. Achievable means accumulation point of what's achievable in finite graphs. So this is my parameter space. This is my parameter space. And what I want to show is that given a point in the parameter space, that is a pair of constraints, given a point in that parameter space, I want to show that if I look at a large network by means of looking at it at a large scale, so a network on n vertices, n large, but I'm only going to examine that thing at a large scale, I want to show that phases emerge. Technically, or, well, actually more intuitively, what that means is that for a fixed constraint, if I look at any subgraph H, that random variable will converge to a constant as the size of the system blows up. And those constants vary smoothly within a phase. That's part of the definition of a phase. I'll formally define phase in a minute, but within a phase, those quantities vary smoothly, except at transition. So what I'll show is that this edge triangle system consists of many phases linked together by phase transitions. And what I'm actually interested in is not just that, really, but I'm interested in how it's coming about that when I look at the system at a large scale, that really I have so few variables. Remember, I'm looking at a very large network, very many variables involved, but at the large scale, when I'm only looking at these densities, density of all possible subgraphs, there's really only two parameters involved, the edge and the triangle density. That's it. Given those, I can figure out all the others. Somehow, most of the variables sort of are invisible when I'm looking at the large scale. And that's what I want to understand. I want to understand what's happening to this in the system so that going from the small scale where I have tons of variables and look at only quantities at the large scale, somehow I lose most of the variables. That's what I'm trying to understand. Okay. So in this particular example, I'm going to exhibit here three of the phases, and I'll talk about some of them as the talk goes on. This upper dash curve is triangle densities related to edge density by t equals epsilon cubed, which happens to be the relation you get for independent edges. Right? And up here, when you have more triangles than that, it's just one phase. Everything bends smoothly. Any density of any subgraph that I would want in there depends smoothly on my constraint P. But there's a transition across the Radin curve, and over here, for example, I have another phase 2, another phase 3, and in fact, there's infinitely many phases along here, which we don't understand yet. We seem to understand pretty well everything going on in 1, 2, and 3 and their relations. I'll say a little about that today. Okay, so again, I'm interested in the emergence of the phases, and there are sort of a couple of reasons I'm interested in doing that. First, I think of this as an extension of extremal graph theory. So the boundary of this phase space is a subject of extremal graph theory and was solved with that in mind. That is, if you fix an edge density over here, say, and you want to know how many possible triangles you get, well, you look, it's the boundary up here, it's the extremum up here. Likewise, you fix a edge density over here and ask not just what's the largest number, what's the smallest possible number or density of triangles you get, it's what's down here. So extremal graph theory has studied these boundaries, the extremum values of pairs or triples of constraints. And what I'll be talking about in here is an extension of that to the interior. But I don't, so in extremal graph theory, not only do they determine what's possible in terms of values, but how it's achieved, what kind of graphs achieve densities like on this boundary. You can't do that in the interior. It's just much too much information. What we learn in the interior is, for a given constraint, a given point in the interior, what's a typical graph that has those constraints. Typical with respect to a uniform distribution, as I'll say a bit more about that. Okay, so that's one way, one reason for doing this is to understand, is there an extension, a rather natural extension of extremal graph theory. There's a very different one which I'll be spending a little more time on, namely, once I understand how these phases are emerging in this system, well, emergent phases actually appear in lots of settings, not just dense graphs like this. And one can be hopeful that lessons that you get from this you can import into other settings like, well, sparse networks, random permutations, even statistical physics, and I'll discuss that. Okay. One point I'll make, and I'll come back to it a couple of times, I want to emphasize the distributions I'm talking about are the following. I fix my densities of a couple of things, edge and triangles, say, and then I take uniform distributions. So it's a family of uniform distributions. There are other ways to get random graphs, right? And it's more common, say, when you're talking about edges and triangles, to use an ergom, to use an exponential distribution. And when people do that, they talk about phases and phase transitions. Has completely different meaning. We're using the same words, but it has very different meaning, and I'll try to get into that later. Okay, so let me try to formalize this a bit. So what I mean by a phase, it's a region, open connected set in the parameter space, in that Rasbarov triangle, say. It's an open, it's a region in there for which, for each point in that phase, there's a unique graphon associated. It's associated by being an optimizer for the constrained entropy. I'll talk about that. Okay, so that's what I mean by phase. Well, a little bit more. So within a phase, I have a unique entropy optimizer associated with each point, and densities of any subgraph at all will vary smoothly. You can compute those densities. Once you have that graphon, the point of a graphon in this kind of modeling, the point of a graphon is it allows you to compute densities. That's what it is. That's all it is. It's a method for computing densities of all subgraphs. Okay? So within a phase, all of these densities vary smoothly within the phase. That's the definition of a phase. It's a set of points for which there's a unique graphon associated, and all the densities vary smoothly as you vary the constraint. The uniqueness is very important here, very important here. Intuitively, what's going on is I'm interested not just in the phase as you vary P, things vary smoothly, but also the transitions. That is, there are going to be places where when you try to vary P, things don't vary smoothly, and that's where there's a phase transition. Well, if I don't have one-to-one between points and graphon, then as I'm varying the P, I'm not really varying graphons anymore. I may be saying something about what's happening in my probabilistic model, but I may not be saying anything about whether graphons are changing smoothly or discontinuously. So that's what's important about this one-to-one. It's transforming perturbations in my parameters into perturbations of graphons. If I don't have one-to-one, you lose that. That's what you lose in ergms. Okay. And in particular, notice this, saying that is, as I explore my phase space, I really only have the two constraints. I have edge and triangle density. These are my only parameters, my only variables, and yet I'm understanding the system at a large scale. That is, I can compute all the densities of everything, just given those two things. So somehow or other, I have gone from all the degrees of freedom at the fine scale to just these 2 degrees of freedom somehow, just the edge and triangle density. And we'll see sort of how that comes about in this setting. It's something you actually can't see what's going in, say, statistical mechanics. Okay? You can't really see why you're getting that loss of variables. Okay, so again, for me, the graphons are a means of computing densities. Why, or how do I think about that? Well, for a large graph G, the way I would compute, say, the density DC4, the density of a 4-cycle, is just use the 1s and 0s in the adjacency matrix and sum over that. This is just dividing to give me my density. Okay, it's a simple thing. A graphon, I think, is a function on the square, unit square, and one thinks of the edges of that square as just sort of infinitely many vertices, sort of taking a limit of the adjacency matrix to get that. We scale down, but that's sort of what a graphon is. And so you can compute densities in the asymptotic limit. The whole point of using a graphon formalism to model the limit of the system is that I can compute those densities in the limit by simply just taking the limits of these sums, and this becomes my dx1, dx2, dx3, dx4, and I get this. So I know how to compute the densities from a graphon. So again, what am I interested in? So in this formalism, I'm interested in phases, and I'm using graphons to be able to compute these densities. And not just any old graphon, but for each constraint P, I have a special Q sub P, a special graphon associated with it. In the physics literature, this would be the Gibbs state. So I have constraints, say temperature and pressure, and given those constraints, I have a Gibbs state with those parameters, and from that I can compute all the properties of my system of very many atoms. I can compute its mechanical properties if it's a solid, et cetera, et cetera. So I need to talk a little bit about how you get that QP for a given constraint. So given a constraint P in my triangle, we determine the Q sub P through a certain variational principle. So let me back up and first just go through the intuitive meaning of the entropy. You start with the partition function, which is simply a counting. It's the number of graphs on n nodes, Zn, number of graphs on n nodes, with the constraint that the density of edges in triangle in this particular model are approximately P, approximately up to delta. Okay? So what am I doing? I'm treating all those graphs, the graphs that have approximately these densities, I'm treating them all as equivalent. I'm just counting them, and so effectively I'm just using uniform distribution on those. Okay? One can prove that Z grows as a function of n, like e to the n squared. So taking the log and dividing by n squared, you're interested in this limit. That'll be the growth rate. And you take the limit as delta goes to 0 because you don't need it at the end. You can easily show that this exists. This is not a problem. But what I'm interested in is, again, I need to understand where this QP comes from. It comes from optimizing this SP. SP is what? It's the growth rate. So it tells you how, how many graphs are have given constraints. Consider the following representation of SP. This is called a variational principle. You can compute S as a function of P by doing the following. You take this quantity, which is sort of recognizable as a Shannon entropy of some meaning. Entropy is used in two very different ways in this talk and in research. You take this Shannon entropy, which is defined on any graphon, and you maximize it among all graphons that have the right densities. If you do that, you get the largest value of this thing, and it'll only depend on the P, and it will give you SP. Okay? So one proves this representation of SP. SP can be understood or obtained by maximizing this function over all Q that have these constraints. Recall that in a phase, for each P in a phase, there's only one graphon, meaning in this maximization problem, there's only one Q that actually attains the maximum. Okay? So when that's the case, that's my QP. So in a phase for each P, there is, by definition of a phase, there's only one QP. So now I know what the QP is. It's the unique optimizer of my Shannon entropy among graphons with those constraints. That's what it is. That's what my QP is within a phase. Okay? So SP is simply the Shannon entropy of that graphon. And then once I have that graphon, I showed you before how we'll compute all densities from it. I can say everything I want about the system at a large scale, everything I'm interested in on a large scale. That is, I can tell you how to compute the density of any other subgraph asymptotically once I know that QP. It's a very simple formula. I showed you the formula. It's a simple integral. Okay? Okay. Now, so this is the formalism, and one of the main results of this series of work, I said on the first page, this is, what I'll be talking about here is all joint work with Rick Kenyon, Qui Ren, and Lorenzo Sedun. We've written, 6 papers on this with at least 6 results, right? But one of the main results is the following. For most constraints, QP is in fact unique, so you actually are sitting inside a phase, not on a boundary. On a boundary, you may lose uniqueness, okay? May or may not lose uniqueness. But within a phase, you have uniqueness. So for most constraint values, you actually have uniqueness. But much more interesting, the graphon is of a very, very special kind. It's what we call multipodal, which means that the set of vertices splits up into a finite number of clusters, and the function, the graphon, is simply a piecewise constant function. You're familiar with this in other language, which I will use in a minute. So let me illustrate this with one of the phases in the edge triangle model, phase 2. In phase 2, what I want to tell you is, what is the optimum graphon like for each point P in this phase 2? Well, here's what it is. As a function of x and y, it's piecewise constant. For these vertices and these vertices, it's this constant, which depends, of course, on epsilon and tau. But for epsilon and tau fixed, this is just one number between 0 and 1. There's the same number up here, a number here, and automatically the same number here, because these graphons are just adjacency matrices, and so it's symmetric. Okay? But there's a lot of special symmetry in this phase. This is a half, which means I've split all my vertices into 2 equal-sized clumps. And there's an extra symmetry here that the probability here is the same as the probability here. That's special. Okay, so I give you the formula for what the multipodal graphon was like in here, and they're similar in the others. Over here, in 1 and 3, they're again just bipodal. That is, you break up the vertices into 2 clumps, but you don't have the same symmetry in these other phases. And we don't actually know the formula. We do know uniqueness, et cetera, but we don't have the formula. Okay, so what this is saying is that the parameter space breaks up into a union of phases. That's what I meant by saying for most of the parameters you have unique graphon. You actually have, for most of that space, the parameter space, it's actually filled with phases with just curves that are separating the phases. And, well, think about what is going on in like phase 2. In phase 2, I had really there, if you think of that as a tool for computing the densities of things, that's just a stochastic block model. That's all it is, right? So what we're saying is that the edge triangle phase space breaks up into stochastic block models, but it's not quite just that. Well, first of all, even that's kind of interesting because in the stochastic block model, you typically are assuming that. You assume that the way you make edges is by this simple formula. But I didn't assume that at all. All I assumed is that I was trying to find out what a typical graph looks like if I fix the edge and triangle density. That's all. And it turns out it is a bunch of stochastic block models. That's what is a consequence, which is quite different, right? And it's not just stochastic block models, but it's a whole set of them tied together with phase transitions. That's one of our main results. Okay, so now what am I going to do with this? So let me talk a little bit about this in other settings. So first, so what I want to talk about here is how I can use this to understand a little better what phases are like and what phase transitions are like, say, in materials. Okay. Again, equilibrium stat mech is the granddaddy. It's the prototype of phases and phase emergence. That's where it all began. It's how we understand it. And that's what this is all modeled on. Okay. But in fact, it's still very much a mystery why it is, or in what sense it is, that in a fluid phase, that system of molecules, when looked at the large scale, loses all those variables and is just, temperature and pressure, just a couple of parameters. How that's happening, what's going on. In the solid phase, it's much better understood. So let me actually pin this down to a specific question. So Landau in the early 50s, actually, this is just a reference, pointed out how important symmetry is in phases and phase transition. This is a quote from Phil Anderson, very good condensed matter physicist, Nobel laureate. The first, what Anderson calls the first theorem of solid state physics is that you can't change symmetry gradually. Given a symmetry element, it's either there or not. So, therefore, using this intuition, this shows why there shouldn't be a critical point in the fluid-solid transition. So, here. This is what the phase diagram looks like, the parameter space for a simple material, where I use a mass density and energy density instead of triangle density would be my edges, say, and mass density would be my edge density. This is what the phase diagram is like there. You have a fluid phase out here and a solid phase here, and they're separated by coexistence. You do have a gas phase here and a liquid phase here, and if you try to go straight across by either fixing the temperature or energy, you have to go through a phase transition. But this is different than this other transition, because you can go from this gas phase to this liquid phase by actually first raising the temperature and just going around the so-called critical point. There is a critical point in that transition, which means that the gas and liquid are really just names that we're giving sort of to pieces of the one fluid phase. There's really only one fluid phase. There isn't separate gas and liquid phases. They're all connected together. You just have to take a path that doesn't restrict your temperature, right? Well, why can't you do that here? It's an experimental fact. This was found by Bridgman in the early 1900s, that you simply cannot go from the fluid to the solid smoothly. You just can't do it. Experimentally, you just can't do it. You have to go through a transition. Why? And Landau gave this argument. You can't do it because there's a symmetry difference. Here, this is a crystal, and this is a homogeneous fluid, and they have different symmetry, so you can't do it. This argument is 50, 60 years old. No one has been able to make sense of it. I mean, actually, yeah. So here's a quote from Pipard. This is the argument. It seems a little too straightforward. And that's everyone's feeling, really. There's something right about it, but you can't pin it down. You certainly can't prove it. You can't prove it, okay? But in fact, you see, I think we can use what we've learned from these dense graphs to prove it, I think. I have a path for proving this, at least. And the point is, what we've learned in the dense graphs is that, you see, the phases emerge, both of these, this is a disordered phase, or a non-symmetric phase, this is a symmetric one. And we can easily prove that you have to go through a transition to get between them, because we've knocked it down to finite dimensions. That was the key point. We've shown how, by getting that the optimizers, the so-called Gibbs states, are these multipodal things, there's only a finite number of parameters. Once I've done that, I can prove it. Okay, so, but notice that even in the unsymmetric phase, I really have a phase. That is, it's still multipodal. It still only has, most of the variables have disappeared already, even though there's no symmetry, most of the things. So that is, I think, the right way to handle this problem. If you want to understand why there is no transition, why you have to go through a transition, you have to first understand why this is one phase, where all the variables went. In a solid, you already know. It's a crystal. Intuitively, once you know you have a crystal, you've seen that you've lost most of your variables. But in the fluid, it's not so obvious at all. But that's actually what one has to solve. First, figure out why a fluid is a phase, where most of the variables went, and then we can use the other argument to actually see that you have no critical point. So, okay, sort of end of, am I out of time, pretty much?
2 minutes.
Oh, that's 2 minutes, a lot of time, a lot of time. Okay, so let me just say a word about the difference between phases and phase transitions here and what's going on in exponential random graph models. In exponential random graphs, instead of taking constrained uniform distributions, you use exponential distributions where, you know, you have these conjugate parameters, the betas, instead of the edge densities, okay? And this is widely used, and rightly so, for small graphs in social sciences, et cetera. But when you try to use it asymptotically to understand large systems, you have a problem. You can do most of what I did before by looking at the Helmholtz free energy and taking the free energy optimizers as graphons. The trouble is, if you have different points in the phase space, my phase space is now the beta space, if you have two different points, they don't necessarily generate different optima. So as I vary my parameters, I'm not varying my optima at all. In the worst case, this is a cartoon of the phase space for the edge 2-star model. In the ergom, all the free energy optima only give edge and triangle densities on this one curve, one parameter's worth. I'm using two parameters in my model, but in fact, all my optimizers are in fact, if properly done, expressed by one parameter. So all those phase transitions or whatever that I'm getting by moving around my two parameters, it's all fake. It's not fake, but it's not saying anything about the graphs. The graphs are not interesting at all. They're just Erdős-Renyi, in fact. All it's saying is that I have a complicated two-parameter way of describing a simple thing, and those singularities are because I've made a complicated way of modeling a one-dimensional thing. Okay? And I'll stop there.
Any questions?
If you add more constraints than just the densities and triangles, does everything go through for the?
Yes. Yeah.
Are they still block models?
Let me say a word about this. Actually solving any of these, well, first of all, as you can see, it seems to start off with the extremal combinatorics. Well, this is a very hard field. There's almost no models that are solved. I showed you a couple of models that are solved, but that's almost it, They're very hard models. And we're taking that as sort of the starting point and then trying to go in the interior. So it's hard to do a lot of modeling.
But you can show that the uniform distribution over the constraint is achieved by, like, is represented by a block model.
Yeah, so in the edge 2 star, K star, yeah, we proved that. Yeah.
So your description in terms of entropies, does that allow you to prove, let's say, exponential concentration of various graph quantities under this uniform measure fixing triangles and edges?
Very, very good question. Very good question. The way this has all been put together, I said, I think of it, okay, I'm trying to understand models at a large scale, but I've chosen how I want to understand that thing at a large scale. I'm taking densities of subgraphs. That's it. That's what this modeling does, right? If I'm interested in connectivity, stuff like that, I'm going to have to use different kinds of constraints. I may have to have constraints on degree, whatever, and then, I'll have sparse graphs, whatever. It'll be a very, very different game. So
what I meant was, do you, for example, have large deviation statements about the number of
well, yeah, that's how we derived the variational principle, was from yeah. The large deviation. The large deviation, the large deviations in this dense setting comes from Chatterjee and Radin. That was proven by them for general dense things. If I put in constraints on if I put in other kinds of constraints, I may have to. Well, I need a different large deviations, which is not available. I mean, yeah.
Didn't Lubetsky and go much further than Chatterjee and Radin?
Further in what sense? In what doing what?
Proving much more detailed results.
About.
The whole.
Now, what I have seen, so I obviously don't know all their work. I'm not, I've seen some of their work. I've talked with IL recently about some of the. So they do sort of halfway in between. They don't do the work I'm familiar with is not ergom work, but sort of canonical ensemble, where they take one of the parameters is fixed like an edge density, but the other one puts in a parameter for. And those suffer from the same defect, though. They are, again, they're really studying the probabilistic modeling. They're not actually studying the graphs. That's the difference. That's the difference. If you really want to understand the large graphs, if you want your parameters to actually reflect what's going on in large graphs, you have to have a one-to-one correspondence between those constraints, and you don't have that in any of these exponential modelings. And the basic fact is that the entropy that I talked about here, the constrained entropy, it's not a convex thing. And so when you take Legendre transform, you lose information. It's only when it's convex that you have sort of equivalent ensembles in StatMech. And it's just not true in this or generally in mean field-like models. And so you shouldn't use those ensembles in mean field models.
Okay, let's thank all 3 speakers.